Hello, बोलते को जियो वाला नया ढूंढ हाँ जी हाँ जी हाँ जी हाँ जी ओ मैं वो गलती तो मैं उन्होंने लिंक किया हाँ जी फ्राइडे दोनों में हाँ जी हाँ जी
I don't think the internet connection is working.
Yes, sir.
The downloads. Well, I've tried to download, all hasn't come, and it also doesn't open the file itself. So
It's working.
So guys, we have some internet issues.
Yes. No, you're good.
We need, certainly to start off with, we need 7. That one. That one. Yeah, that's better. It took 10 minutes to go 100 KB. Yeah. And we should be able to start shortly. Yes, we're there. Okay. Thank you all for your patience. We had some internet problems and I couldn't download the materials, which makes it really hard to talk. Probably a little bit much because we've got some movies into the first presentation. So first, I hope that you had a good day yesterday. I thought it was excellent doing some hands-on stuff first here and then seeing the nice 3D printing facilities that are on campus. So I had a really good day and I hope you really enjoyed the diversion from just sitting in the lecture room and listening to the lectures as well. Before we start with the content of today, I promise you I'd let you know what the exam will be about today. And I'll give you 2 options. So I've got 2 papers here. I emailed them to Professor Malik and he'll distribute them among the group. Please get together in a group of 3 or 4, and for those people that are through Google Meets, maybe it's the easiest if you all get together in a group and we'll just talk for 5 to 10 minutes together about one of those papers. So I can ask you some questions about what's the microfabrication approach that has been used, what is the innovation of this paper, is it compatible with upscaling manufacturing or not, is it a complete system, or is it just a module working towards a larger aim in the future? The 2 different papers that I picked are from 2 different types of journals. One comes from Biosensors and Bioelectronics, which has got a little bit more of an engineering focus. And one comes from The Analyst, which is an analytical chemistry paper. So I'll leave it up to you and your group to decide which one you'd prefer to be reading. They're fairly similar, have similar aspects. There's some things where they're different. And the key differences is that this one talks a little bit more about engineering and instrument design, whereas this one talks a little bit more about analytical chemistry and method development.
On the list I can circulate.
Yeah, so I emailed the PDFs to you, so you can circulate them to the group in case there's not easy journal access. So they should be ending up in your inboxes sometime today. So yesterday we already learned a great deal about 3D printing. To do a little bit of a recap, in 3D printing we start off with a computer drawing. This computer drawing is then being sliced into individual layers for later printer. And these layers are printed one after another to form a three-dimensional object. So from one aspect, a 3D printer is just a normal printer. There is a computer drawing or a bit of text being sent to it, and wherever the text or the computer drawing's got lines, it deposits an ink or material. The difference with 3D printing is that it doesn't only do that once, but it does it over and over and over again with different images. And that's where the slicing comes in, because every object gets broken down into hundreds of slices across its set direction. There's a wide range of 3D printing approaches available. In microfluidics, the most popular ones are FDM, two-photon lithography, stereolithography, and inkjet 3D printing. And we'll be talking a little bit about lamination today as well, and some powder printing. So just summarize what 3D printing is, and it's again in this slide. We start off with a computer-aided design. Projector so that people can watch along. There we go. So we start off, well, as we heard yesterday, we start off with an idea. Then we put this idea into a design where we give it dimensions. So it's important to know how high, how deep, how wide, is it going to be round, is it going to be square? They are all the design considerations, and they all end up in the CAD model. CAD model is then sliced into an STL file, which forms pretty much the blueprint of the printing. The STL file, then using another bit of software, is converted into the G-code. And the G-code, we had a quick look at it, is the layer by layer instructions to the printer to deposit it one after another. So we do the 3D printing process. Once the product comes out of the printer, with some of the printing types, we need to do some post-processing. We've heard yesterday a little bit about support materials being in there. We've seen the movies with the powder. So sometimes we need to do some cleaning up as a post-processing, and then we get our object into our hands. There is a wide diversity of 3D printing techniques, and through most of them, all but one, we'll be talking about, because the powder printing is not most relevant for 3D printing, even though I do have a slide on it, because powder 3D printing has become really useful for printing other tools and things in the lab, so holders for your devices. If you want to interface with a mass spectrometry, maybe you need something to hold your capillary in place and your electrode. And increasingly, powder printing is intruding into the laboratory space, not necessarily for the microfluidic devices, but to just hold the rest of the instrumentation, particularly when it's custom, to hold it in place. So we've got fused deposition modeling, or FDM. We've got direct writing. We've got stereolithography. We've got lamination. Where's my lamination picture? It's powder. There's lamination. We've got selective laser sintering onto a laser bed. We've got here the digital mirror projection 3D printing, another form of photolithographic with the inkjet printing. So the material is first deposited and then cross-linked with the UV light. We'll be going through them quietly, one by one, starting off with FDM printing, which is going to be an easy start to the day because we already saw the 3D printer, the FDM printer yesterday. So what we have in FDM printer is that we've got a spindle that contains our material that we're printing. The mode of printing is that we're feeding in the thread and we're melting the plastic in the nozzle to be able to mold it and deposit it onto the plate. This puts a requirement on the materials that we can use for FDM because they need to be thermoplastics. The FDM material, it comes in on the spindle where it's a solid. It then needs to be heated up to turn into a liquid. So it needs to be a thermoplastic. For example, PDMS is a two-component polymer which is not a thermoplastic. It can't be printed with an FDM printer. So there's different prints for different polymer types. This is one that's used for thermoplastics, which is very nice because thermoplastics are also used for hot embossing and injection molding. So if we can use an FDM printer for printing microfluidic devices, it means that we are working in a material that is compatible with upscaling for large-scale manufacturing. There is an incredibly broad range of plastics available. In one of the later lectures, we'll be talking about microfluidics being printed, functional integration. There are materials available in a wide range of colors, including transparent, which is very useful for microfluidics. There are materials available with different levels of conductivity. There are materials available with different kinds of porosity. There's materials available with thermogrower properties. And there's materials available that can be sintered after the printing process. So FDM is very popular. There's very affordable FDM printers available. And FDM printing is the printing type that an increasing number of people have taken up at home as well, to just print parts that are missing or custom designs. An example of an FDM printer sitting here, which is the MakerBot, which you can see in a lot of places, where here we've got the print head, which contains a heating module that communicates with the computer. There will be a pulley in here as well to pull the fiber down, which is molten in the heater in here, and then comes out of the nozzle. Typically, the nozzle size is 0.4 micrometer or 0.4 millimeters, 400 micrometers, which is the nozzle that we've seen used yesterday. 100 micron nozzles, 0.1 millimeters, are available as well, which allow for the printing of finer detail to the cost that it takes a little bit longer. What can also be done with 3D printing is that you print a mold that you then later on use for casting PDMS. So you don't necessarily need to FDM print, or this is relevant to all the 3D printing techniques. You can also print a positive structure that you then pour PDMS over to replicate the structure that you've printed. Now, I particularly like this paper because they've printed a microfluidic toy box with very cleverly designed interconnects. And these interconnects can be put together before casting, which then allows them to not only print a mixing unit here or a splitter, but it allows them to just put them together before they cast, which I thought was a really clever way about going in a modular way. Is ensured because all the connections will become little reservoirs. So I thought this was quite here using multiple extrusion heads, which is a bit, let's see, alternate their calcium to then get the gel formation of the alginate jelly to be forming down at the printing nozzle. One of the much more interesting application of this direct writing printer is that you can also feed cookie dough in it and cake batter. So you can actually print cookies and cakes, get them really pretty designs before you put them into the oven. Again, things don't need to be microwaved, but this was the very first printer that I got into my office and I had to assemble by hand and get it to work. So alginate and self-healing polymers are a really good option. The nice thing about these printers is that you can also use them in a liquid environment, and that's what's been done here. Here they had a non-cross-linked, highly viscous matrix. They went with the print nozzle in there, and they deposited an immiscible solvent in the viscous polymer matrix before they cross-linked. After they cross-linked the resin, they could get the non-cross-linkable resin out. And as you can see, a very intricate three-dimensional network was drawn by just depositing, almost like a syringe pump in 3 dimensions, depositing a non-cross-linking agent in a jelly that was made from a cross-linking agent. So direct writing, not very high resolution, but can be, it's not the 3D printing approach that works in a layer by layer manner. You can actually move the position of your nozzle in all 3 dimensions, and through that create very complex networks like you can see here. So that's what can be done with direct writing 3D printing. The setup, as I just said, it looks very similar to an FDM printing. The difference is the printhead. The printhead is not a heater to melt thermoplastic, but it is just a nozzle where liquid comes out. The liquid can be cookie dough, it can be chocolate, it can be alginate and calcium to cross-link into a gel. It can be a non-cross-linkable liquid that you can then deposit in a gel matrix before cross-linking. So there's a whole range of different direct writing printers that have been made tailored for specific applications. And those applications, 9 out of 10, are in the range of cell culture, which is an area that we don't really touch on. The next part of 3D printing is SLA or digital light projection. A D there, first D there should have been an S. So we've got stereolithography, which is an approach where a laser is irradiated on a scanner system, which contains some mirrors, and then projects it down into a bath to write the structure in one layer, then pick here containing the transform containing object is lowered a little bit, and then the next layer is being written using the scanner system here to move the laser around. So that is stereolithography, which is a vet-based, resin-based 3D printing approach. The alternative that is based on exactly the same chemistry, but is a little bit quicker, is digital light projection, where instead of having a single laser beam that is being projected to different areas in the build space, there is a digital mirror device. Here's my mouse again. So a light source, which could be a laser, but also could be a mercury lamp, for example, or UV LED, is irradiated onto a digital mirror device. Digital mirror devices are traditionally made for projectors. So the light that's coming out of our projector here at the moment, we see the feature that we see because a digital mirror device is reflecting certain bits of light towards the screen and other bits of light not. So the digital mirror device goes through a lens, projects onto the resin bath, and as you can see here, this printer is upside down, which is called printing in the bed mode. The image is projected onto the resin bath, forms on the bottom of this pick. The pick is taken, lifted up by the layer height, which could be as small as 2 micrometers. It could be as much as 100 micron, depending on how good and expensive your printer is, or when you bought your printer, because the layer height is decreasing rapidly with advances in the development of printer technology. So we get the light source, we get a digital mirror system to project some bits of the light ahead through the lens into a bath and some not. The lens parts that are on and project the light from our image and cross-link our resin into our pic. So the hardware that you need for a D-build printer is a light source for photo initiation, which could be, I already said, could be a laser, could be a mercury lamp, could be an LED. It also could be a mercury lamp in combination with an LCD. So it doesn't necessarily have to be a digital mirror device. The cheaper, more budget printers actually use an LCD screen, as we all have in our phones, to have black areas where the light is not going through, and transparent areas where the light can go through. We can print normal direction. You can see here where the stage is lowered through the print process. Or we can print upside down in bed configuration, because beds the animals are already hanging upside down on the ceiling. Doesn't matter for the print process. The advantage of printing upside down is that you can pull your printed object out into the air. You don't need to look present. If you want to print a high object when the stage is lowering down, you need to have a very deep resin bath, which, if your resin is expensive, may be financially not really viable. The chemistry in DLP, because we do photo cross-linking, we do form the polymers using photo polymerization reaction. The resin chemistry is really critical to the outcomes that you get. You can buy resins just ready to go online or at the 3D printing shop. The nice thing that there's not a lot of IP protection around DLP, and it's very easy to make your own resins and tailor your own resins, which provides great opportunities for enhancing printer performance, as well as using it in your research if you're in the area of material development. There's a huge variation of DLP printers around. The Bristol microfabrication one that's pictured on this slide. I'm very pleased. I recently got funding of about $1 million Australian to get one in my lab. Very expensive printer. It almost looks like it comes with a coffee machine, comes with an integrated computer, nice vibration isolated print table. It's got absolutely fantastic specifications. The build size is 5 by 5 centimeter. And it chopped off the resolution. It's got a 2 micron pixel size with 2 micron layer height, which means that we can print microchannels that are about 10 to 50 micrometers. So it can print really, really small detail. Life, however, doesn't need to be expensive. Most of the work that I'll be talking later on was done with a frozen shuffle, which is what I just said, an LCD-based printer. So it doesn't have a digital light projector in there. It does have an LCD screen and a mercury source to project the light into certain areas. But the frozen shuffle, we got a bargain as well. For 15,000 rupees, you can have a printer in your lab. So this is a very affordable printer. This is a version, it's at the moment so cheap because they have upgraded their version, but even their newer printer is only 30,000 rupees. So these are not very expensive printers. And you can still do very, very similar research with them compared to the very expensive printer that I just got. The nice thing is, if something goes wrong in your research, you're working on materials, you may break something on the printer. Replacements part, fixing these printers is a lot easier. And even if you completely destroy the printer, your supervisor is not going to be sitting and crying in a corner somewhere because it hasn't been a major investment to get this type of printers in the lab. So they're very accessible. From a price point of view, they're very easy to modify because they're not very complex put together. They come with one standard set of software, but there's a whole suite of other open source software packages that you can get access to if you want to change something on their settings. So we're quite pleased with the frozen printers for research purposes. On the resin development, we've got this afternoon a complete session where we only will be talking about resin development because there's a lot happening in the chemistry there. So we'll be going into a lot more detail on how we develop the resins for DLP And then the second session this afternoon, we'll be talking how we can use digital light projection to play with material properties to achieve functional integration in them. Laminated object manufacturing is another way of 3D printing. And what we have here is a roll of a polymer with an adhesive where the rollers are displaced, a laser beam cuts the material, patterns it in a layer by layer manner. Then a hot roll goes over, sticks it all in place. I think we may have an internet problem again.
Yes.
Ah, they were not watching along. Sorry, guys. Where's my mouse? There we go. So we've got the material is rolled over, stuck in place with a heat-activated glue with a roller. Parts are removed with a laser. Stage is moving down, next layer comes in top, and that goes over and over again. The cutting in the first example, it was done with a laser. It can also be done with a knife, with a scalpel or a blade, like in scrotography. You can see here that parts are cut out. Initially, during the print, they still stay in place, but that's the point where you need some post-processing to remove the areas that are cut out later on. There is a microfluidic version of laminated object manufacturing, which was developed in New Zealand. There's very little information available of what it does. It works with a resin that's 5 micrometer layer height. It's got 5 micron resolutions. And here you can see a couple of different mechanical components that have been printed with it. Other than that, there's not a lot of information available yet. So this is a very recent development. We already briefly touched this on this technique yesterday. We've got inkjet 3D printing, which is very much the 3-dimensional equivalent of the inkjet printer that you may have in your room at home, or may have sitting in the lab. So we've got an inkjet nozzle. It sits here, which deposits, it sprays the ink into the place. The difference is that when you've got your printer at home, it's got black ink and magenta and yellow. It doesn't have colored inks, but it's got inks that have a photo crosslinker in there. So after the layers have been deposited, the light goes on, the UV-initiated polymerization reaction takes place, which crosslinks the printed layer, which then allows for the printing of the next layer on top of the cured initial layer after the platform that you're printing on has been moved down. So you can see a huge synergy between all these 3D printing techniques. You print a layer, you move the stage. You print another layer, you move the stage. The stages that move up, stages that move down, but 3D printing, they all share that layer by layer approach to manufacturing. So the material jetting is a form of the inkjet printer where rather than one nozzle at a time, you've got a whole array of nozzles where the material falls away. You print 2 different materials actually at the same time. One that does contain the crosslinker, one that does not. The one that does not contain the crosslinker is the support material. So it takes up place, which allows us then to print the overhangs, as we heard yesterday. And the support can be removed afterwards by hand, or some of the materials need to be dissolved in a little bit of sodium hydroxide. The removal of that support is not a problem for most large objects, but it may be really difficult for small and long microfluidic objects, because the support material it's removed by a dissolution process. Dissolution, if you've got a 5 centimeter long, 50 micron Capillary, it takes a very long time for your agent, your dissolution agent, to actually creep all the way up that channel. So the post-processing for microfluidic devices made this using this approach, maybe 1 or 2 days of soaking in a beaker with a reagent till the reagent has really found has been able to dissolve the support material far away in the corners. So we looked at this movie yesterday. I hope it's come along. So this is a movie on how the 3D printer worked, where you can see that the print heads print the material, and straight after the light cross-links the polymer. You see the droplets of ink, just like in an inkjet printer, coming down in a layer by layer manner. The material is being cross-linked, and we get the objects being formed. The disadvantage of the PolyJet printer is that it's a very highly proprietary materials. So you can't use any materials that you develop yourself with that printer, because you avoid the warranty. And you're talking about a $500,000-$600,000, so a very expensive instrument. The other problem is that the resin is quite expensive, and it's got a very short shelf life. So once you've got it opened, you've got 1 or 2 days to finish it all. Particularly for the microfluidics fields, we print very small structures. So we only use very little resin, yet we have to use 1 liter of resin once we open it. We need to finish it, because otherwise it's expired before we want to reuse it again. And again, if your resin is expired, you still use it, you void the warranty of your printer. So beautiful prints, very reliable, but not very cost effective to have as a research instrument in the lab. So if you want to use PolyJet material for some research projects, I'd suggest use a commercial print shop. So the 3D printer devices, you can either have the printer yourself on campus, but there's also a lot of print shops that offer print services. And it may be a lot more economically viable to use a printing service, because they don't have the problem with throwing out a lot of resin, because they do a lot more prints than you would do as a small research group. But the nice thing that the PolyJet does offer is that you can print multiple materials in one go. So it's got flexible materials, it's got different colors, transparent materials. So you can actually print functionally integrated devices. For example, flexible material is absolutely great and has also been used for integrating these pneumatic valves. So, and that then opens an option for fluid control and the integration of pumps. So there's really great features that you can do with the inkjet printer. But if you're like doing research on the material side, it may not be the printer for you. Yeah, got the disadvantages there. The next is a little bit of an out there 3D printer, but if you think about engineering, microfluidics, integrating it with electric components, I thought it would be worthwhile being aware of this printer as well. And this is one that can actually print the whole circuit board. So it's a Dragonfly, and it allows you to print the electronic interfaces, as well as some insulating hollow areas that may contain a microfluidic device as well. So it's the only printer that is focusing on printing electrodes for flexible electronics design. You can see the print process works very similar. We've got a photopolymer that's being deposited, and then a light that cross-links. We've got different slices for our objects being printed. And you can see that you get an electronic board that you normally would make with an etching process. You can actually make that using conductive and dielectric inks. And last time I spoke with someone that knew, they were also talking about integrating some insulators in there that would then open up the options of combining voids or microchannels directly with these conductive and dielectric materials, which then provides great opportunities for the printing of functionally integrated devices in one step. So it looks like a normal etched printed circuit board, but you can print it, and that again, if you've got access to a printer, allows for a very rapid turnaround. So looks like a normal printed circuit board, but it's printed and not etched. Multi-layer devices. Expensive printer, but if you're in the electronic space, a nice one to be aware of that it's around. So here we've got the properties of the Dragonfly printer. It's an inkjet-based printer, so it jets the conducting or dielectric inks to fabricate both the circuit board itself and the conductive traces, and it can go, I suspect that's not 0.3 micrometers, I suspect that's millimeters, it's not that small. It's got a proprietary ink that's based on silver nanoparticles to have the conductivity, and again, an LED light source, UV light source to crosslink, and the most of the nanoparticle-based inks, they also need high energy to be sintered to actually remove the polymer matrix from in between the nanoparticles and create a conductive material. Another nice thing, if we start talking about functional integration, is that it allows for print pulse prints. There's a couple of different ways that we've got for integrating existing components in 3D printing. One is during the assembly, so you print your objects. For example, you would like to have a membrane in there, so you print your microchannels all enclosed. You then, with some super glue, assemble a commercially available membrane in place. That's post-print functional integration. If you can do print pulse prints, that means that you can print half of your device, introduce your membrane or your other component that you want to add, and then resume the printing process with that functional part being integrated, which is a very effective way for actually embedding other alternative functionalities inside a fluidic device. The ideal way of functional integration would be in print, which means that the functional material is incorporated as part of the printing process without the need for any intervention at all. Then we've got the printer that we talked about, which is the binder jetting, where we've got a powder bed where we print a glue onto the powder to stick it together. And that allows then for the making, the selective clumping together of particles, whereas other particles don't have the glue, and you can brush them away with a brush. The resolution of the binder jetting is not fantastic for microfluidics. You struggle to get anything under a millimeter, but it makes really nice nylon parts in very complex geometries that are not accessible at any other fabrication approaches. One of the people that's working in my team, Richard is his name, he is a mechanical engineer by training, and he services the university in precision machining. So anyone that needs something, some custom instrumentation for small scale reactions, parallel reactions, he designs those instruments. Traditionally, he always used a high resolution CNC machine to mill everything in aluminium, or sometimes in Delrin as a Teflon-based polymer. And he's increasingly now using a powder printer because it allows him to manufacture really complex three-dimensional structures that, with the overhangs, he couldn't machine, or could only machine with great difficulty on his CNC milling. So at the moment, his design process is that he designs all the components that he wants to have, and he then selects some for 3D printing, some for machining using a CNC milling. He sends off the 3D printing to the 3D printing company. He then goes to work in his workshop to do the milling for the parts that need the structural rigidity, for example, or the heat conductivity of the metal. 2 or 3 days later, the prints come in and he assembles it all together. And the nice thing is of the 3D printed components, they've got all the holes and the threads in place for the screwing and assembling it together, as well as little recesses where he can place the printed circuit boards that operate some of the sensors that are on some of the devices. So powder 3D printing may not be directly useful for 3D printing, but if you're thinking about not only building the device, but building a whole instrument, the powder printing certainly is a manufacturing approach to take into account. In particular, because you're all researchers, you won't be thinking about building 1,000 boxes in one go. You want a prototype. You want to make one, try, see if it fits, see if it works, see it's convenient, and then move on to the next design. And that's where the powder printing can be very useful tool. And if all is good, we've got a movie here to see how the iMaterialize powder printer works. You can see it's again computer-aided design. It's a normal print process, but then we melt, cross-link the powder parts together. So there's the powder bed. The object comes out, needs a little bit of clean, but then you can see very nice structures where you can have mass of material if you need it, but you can also have voids in there if you want to save on material or save on weight. So there's a lot of research going on in structural design, in how can you make functional structures that have strength and rigidity, but at the same time are really light. And with 3D printing, you can actually remove a lot of material that is not functional in that aspect as well. So there's droplets of fusing agents along with thermal energy that bind that powdered material together to fuse the layer. After the print is materials, there's an intensive post-processing step, first with a brush and a little scalpel trying to remove all the powder. And then there's a chemical post-processing step as well to make sure the instrument the tool is sealed and looking nice and shiny. All the leftover powder is used for future builds, so it's a very low waste additive manufacturing technique. The layer thickness is about 80 micron, but the minimum feature size is 500 micron. I haven't seen 500. I've seen 700 being. 500 is probably only happening in the engineer's hands. But still, for making threads, making detailed devices, putting instruments together, it is a really, really nice toy. So for the last almost hour, I've told you guys about a whole variety of 3D printers. So I reckon you'll feel a little bit like this person, like, how do I ever start in this 3D printing area? There are horses for courses, and it depends really, really very much on how much money you have, what you want to do, and what scale you want to do it at. So here I made a table with a range of different printers. So we've got the FDM printers in the first row. The minimum feature size, and even though this is a moving scale, I made this table, I think when we started first, Professor Malik and I first started talking, so around COVID. So the minimum feature size then was about 250 micron. I see more and more things in the literature where people are pushing the 100, maybe 80 micron with FDM printing. So nothing in the 3D printing literature is up to date because there's new stuff coming out in the literature every second. Capital cost of FDM can be really low to moderate, depending on the printer that you buy, depending on how much resilient you are to software that may not be very user-friendly, the materials. So the lower end printers may be a little bit more temperamental to operate, may have a couple of bugs. You may need someone with a hobby in engineering in order to operate them properly. Whereas the more expensive FDM printers, it will be all very smooth software interfaces, and you can pretty much get it out of the box and get it to print. Also, if you don't have an engineering background. So costs depend on skill set and the number of print nozzles, but we'll go into a little bit more detail about that later. The great thing about FDM printing is it is the print approach that has been adopted by a lot of households. A lot of people with hobbies, people for using the weirdest materials. So there is a fantastic selection of materials available for a wide range of different providers. There is no support material, so post-processing is very minimal. And there's great opportunities for alteration. We've seen yesterday, you can build your own FDM printer. There's a lot of ways that you can tweak, play with an FDM printer, maybe combine it with other printer types. So it's very open and accessible. Direct writing, we briefly touched on. Minimum feature size is about 100 micron. Capital costs are not really high, but most of them are custom built. So we actually have very few commercial direct writing setups. They're mainly like the FDM printer that we've seen yesterday. Their home build system. The support material is external, so we actually print into the material that we cross-link later on. You can do post-processing, but quite often it's just the removal of the liquid phase. And they are, because they're all custom-made, custom designed, they are very open for alteration. SLA DLP here on the line. Difference between SLA and DLP was the SLA uses a laser to write the structure pretty much like a pen, whereas the DLP projector, it's got the DLP printer has got a projector in there, so it projects a whole image at a time, which means that you can print a whole layer at a time, which gives us a much larger print speed. Capital costs, as I've seen you, the frozen printer was very cheap. The 3D printer I just got funding for was very expensive, so very wide range in prices. Materials that are available are increasing. The good thing is that they're all open source, so you can buy them, both the print materials in a shop, but you can also mix your own acrylate or other photopolymerizable materials together and optimize the settings and print your own materials. There's no support material. There's very little post-processing. For microfluidic devices, the only thing is that you need to push out the resin from the channels, but I'll go into a little bit more detail on that when we have a special session dedicated to DLP this afternoon. Open for alteration, yes, there's a lot of modifications you can do. Laminate object manufacturing, minimum feature size, 5 micron, so pretty good. Capital cost, what I saw was moderate, just over between $100,000 and $200,000. Only one material, so very few materials, no support, very intensive post-processing involved, no options for alteration. There's only one printer in New Zealand. Inkjet 3D printing ends up with 200 micron channels, so not small, but still nice to do microfluidics with. Really high startup costs. So these are beasts of machines that are really expensive. The range of materials that is available, it is increasing, it's getting better. The problem is that where they launch new materials, they take other ones off the market. Imagine you're doing your PhD, you've just started with a material they're taking off the market. All of a sudden you can't get access to the material anymore. So it's a bit of a risk because that as a researcher, you don't have any control on your materials. It's all proprietary. You don't get any information what the materials are that your resin is made of. You don't get notified if your chemistry changes. It's sold under beautiful names like Crystal Clear. So it's a bit, as a chemist, a bit of an unknown box what it's printing. There is a support material in there, which means that we've got reasonable high post-processing work to be done to remove the areas that haven't been printed. Nothing is accessible about that printer, but it is extremely reliable. You send your file, it beeps, it does a little bit of movement, and your device comes out. No failure rate. So very reliable workhorse. And then we've got the powder printers, over 500 micron, very high capital cost as well. Very few materials that you can do, but it's got nylon. Who's not happy about that? It does have a support material in there. Post-processing, very intensive and not open to alteration. And I think I've got absolutely perfect timing because it's time for morning tea. So this was the overview of the printers. We'll go a little bit more into the details about microfluidics in our next session. couple of windows that it hadn't downloaded. Let's just see. I don't know when the power went off after we left.
Okay. Yes, you can check.
No, we didn't. Let's just download only the file because it's. Let's. Another 30 seconds left of downloading. Or 40. Or 50. Missing a D there, but all good. So, session 7.2, or the second session on the 7th day of the course, we're talking about 3D printed microfluidics. For those of you that are joining us on Google Meet, sorry for the interruptions. We had a couple of power outages to deal with. So fingers crossed that the power is now reestablished and I will be able to go through this session smoothly. In the previous session, we've gone through all different types of 3D printers that are around. And right now I'd like to focus a little bit more on how you could actually combine that with microfluidics to use 3D printing as a manufacturing method for microfluidic devices. We talked about microfabrication in general. Where we had photolithography traditional as the basis of all our microfabrication, where we then could do direct microfabrication by using photolithography to create an etching mask, to then do wet etching with hydrofluoric acid in glass and get these nice round under edge structures. The other option was to do polymer processing, still use photolithography to create a template, which then could be used to cast an elastomer, as being done in soft lithography for replicating PDMS devices, or for thermoplastics, where we can use the thermoplastic machining methods, injection molding, or hot embossing, depending on the throughput that you want to have. These traditional fabrication approaches all give beautiful microfluidic structures. Glass etching is great because we get an inert substrate and a material that's known to the chemist. Problem with glass manufacturing is that the manufacturing process is rather laborious. When I was doing part of my PhD at the University of Neuchâtel, that's when I made my own glass devices. It's 2.5 days to make a single wafer. And on those days, most of the time you spend in the clean room, gowned up, waiting for things to bake or to wash. So the actual manual handling, it's not that you're really tired by the end of the day because you've been busy with your hands the whole day. It takes very long because there's a lot of waiting. You need to align the mask aligner, expose for 30 seconds, take it out, do a 15-minute post-bake. It's not worth your time to get undressed from your clean room suit and get dressed again. The cleaning after the HF etching. The HF etching itself takes 45 seconds. But then the HF needs to be rinsed off in a water cascade, and that takes 45 minutes. So there's a lot of really lengthy processes with glass manufacture that are too short to get out of the clean room, and therefore it becomes an expensive process if you have to pay for someone's labor. Injection molding, here we've got an injection molded device. On the picture, it's hard to tell it apart from a glass device. If you've got them in your hands, you can feel the difference in material. There's a much wider choice of materials. It can be automated and it is cheap, provided you've got lots of different devices to make. Problem with injection molding is that it's got very high startup cost. If you want to make an aluminium or a nickel mold, you're talking tens of thousands US before you've got your starting point. And from then on, it costs only $0.01 per device to make it. Then we had soft lithography with PDMS. Very easy to make, transparent device, air permeable, so fantastic for if you want to do some cell culture. Fairly laborious, as every device needs to be made by itself. That means that it was also challenging to automate. And for analytical purposes, PDMS is used as a sorbent in gas chromatography. So maybe for analytical assays, there's a risk that your analyte or some of the reagents actually get absorbed into the PDMS device itself and then leak out, diffuse out later on. So something to take into consideration when working with a PDMS device. So why 3D printing? Consumer 3D printings are becoming increasingly accessible and affordable. And if people can afford a printer for home use, then probably the research group can afford one for laboratory use as well. And it's always nice to just have full control over a toy. If you've got one sitting in the lab, or a little bit less, but if you've got a 3D printing shop close by, it still counts. You can do rapid prototyping, which means that you can think of a design, try it out, point at the things that you don't like, change them, try again. One of my students referred to it as a fail fast, fail often approach. So you get an iterative design, you try it, you know what's wrong, you improve it, you find the next thing that's wrong. And in 2 or 3 days, you actually get a really, really good device because every thinking step, you've actually experimentally validated if it works or not. We've got sub-millimeter resolutions, feasible also for voids. So you could make templates with it. You can also directly print channels. Sub-millimeter is fine. Sub 100 micron was a no-go. Over the past 5 years, it's become very, very accessible. So truly printing microfluidic structures is really within close to our fingertips. Design of 3D printing is no longer restrained to a 2.5 geometry where you draw your design on a paper flat and you just make all your channel structures 50 micron high. All of a sudden, the sky is the limit because you've got access to your three-dimensional space. Problem with that is certainly my generation of people, and I'm not sure about yours, we're not trained to think three-dimensionally. We're trained to think on paper, draw things on paper. So it's actually really challenging, and we need a change in mindset. Now we've got access to the three-dimensional space to actually use it. I did a survey a year or two ago about 3D printed microfluidics. Less than 5% of the devices actually use that third dimension. Most of them just use it as an alternative to PDMS, because that's the way we were all trained. That's the way how we're always thinking. So using that 3 dimension to our benefit is something where there's a lot of opportunity, and where we need your generation to stand up, because you've got a lot more flexible minds used with working in 3D, going through 3D cinemas. So we've got our hopes up as all these, that the next generation will actually step up and truly take the benefits of that third dimension. The other nice thing for if you want to look at commercialization is that 3D printing has got the potential to bridge the gap between prototyping and short-run production. Short-run production is if you want to make 100 devices, so not yet 10 or 100,000, but enough to sell. And that's actually a really hard part for a company to be in business if you're only making a few. And 3D printing is a very nice manufacturing method that you can scale it up a little bit. Certainly for microfluidics, we've done some experiments with printing on an inkjet printer, printing 30 or 40 devices in a print run. You can get to a reasonable throughput per day. So small scale production is actually possible. And then what we'll talk about after lunch is you can do functional integration. You can actually combine materials to get additional functionality into 3D printed devices. So they are the drivers why I engaged in the area of 3D printing for microfluidics in 2013, 2014 is when we started. We, by the way, when we started this research field, all of our printers came from crowdsourcing. So we went on Kickstarter, which is one of the crowdsourcing websites, where new 3D printers were being proposed and developed. And we supported a range of different crowdfunding projects. They got funded, and 6 months later, we got a 3D printer delivered to our laboratory that we could then try and play with. So things don't necessarily have to be expensive. There's actually a lot of instruments or tools that you could use to benefit your research that are available in the crowdfunding space, which is not accessed by a lot of researchers. So the little question mark man on the last slide before we went for afternoon tea was, how do I know what printer to use? We saw that question coming. So at the University of Tasmania, we did a research project where we actually compared apples and apples, and we did a back-to-back comparison of different printing methodologies to print microfluidic structures, to look at how useful are they actually in the microfluidic space, what are the opportunities that they offer, and what are the limitations that they have. So this is the general design that we did most of the experiments with, and we worked with a blue and a yellow food dye to do some mixing studies. So we compared on a couple of different parameters. First was the fabrication. What's the resolution that we can achieve? Not necessarily in the printer specifications, but what are the channels that we can print? Because we found out really early on that having a printer with a 50 micron pixel size does not equate to being able to print 50 micron features. There is a lot of skill required to get a printer to operate close to specifications. And quite often it's the printed features don't have the resolution that the printer does have itself, which kind of also makes sense because we looked at the FDM printer yesterday. The motors that drive the X and the Y movement have a certain resolution, but the liquid polymer comes out of the nozzle. That's got a certain width. So if our printer axis moves with 10 micron precision, but our molten polymer is 400 micron wide coming out of the nozzle and may get a little bit of a wobble on the way down, that 50 micron resolution of the motor that's driving in one direction may not be accurate for what we can actually print. Because first, what we can print what comes out is 400 micron, about 400 micron wide. Then it will flatten out a little bit by the time it gets onto the plate. And if we want to have the motor step only 50 micron to the left or right, we're on the top of our 400 micron sausage of materials that it's just deposited. So print resolution, specifications on the sheet that you get from the manufacturer, and how small you can actually print are very different things in microfluidics. Why we thought it was useful to look at that, measure some channel sizes with a profiler and with the electron microscope. And we also looked at the precision. If my CAD drawing says I want to print a 200 micron channel, do I get 200 micron? Do I get 180? Do I get 250? Huge variation. So what you think you're going to get is not necessarily what you get in microfluidics. So measuring your device specifications is an important thing to do, particularly if you want to do some calculations later on volumes. So our application was in fluidics. So we looked at some mixing and then some flow rates. And we also looked at the scalability of manufacturing, looking at how much post-processing was involved, looking at what the cost was of the materials and of the print time for a device. So we 3D printed laminar flow sheets using an FDM printer. And here we used a clear ABS. And as you can see here, the device has got our microchannel sitting on the little ridge. So we've got first a base plate being put down, and yesterday the little cup that we got printed, it started with a bottom as well. So you first get a bottom colored in because you need to print on top of something. You can then see that the device here has got the channel sticking out. We designed it the way it looks like to save time. Every passage of the 3D printer, we've seen yesterday, every little bit that it deposits, it takes time. Here we only wanted to print this Y-shaped microfluidic channel. So why would we have to wait for printing all the material up here that we're never going to use? So we determined how wide the walls of our channels had to be leakage tight. And that's the size that they were printed here. And then we printed some reservoirs to have our fluid connectivity. And here you can see it filled with a dye. This is not leakage. This is just a little bit of splashing on top because the student hadn't taken a lot of care taking the photo. With the PolyJet, it's a very different consideration in the design. PolyJet printer, it prints the build space that's about 50 centimeters by 40. So a large build space. And it prints it with cross-linked material or with the filler material, the whole space anyway. So it doesn't really matter if we cut down a little bit of our material around our device. And that's why this device in here is printed all the way up with the same height. And we can see here, because the resolution is a bit better, we put numbers in there because that allows us, when we're looking on the microscope for certain phenomena taking place, when do we get good mixing, we actually know that we're 20 millimeters away from our inlet. So sometimes in the design, it's actually useful to have a little ruler there, because when you're looking through the microscope, it's hard to orient yourself where you are on your device. Having a little marker, very early in my PhD, I put a little arrow where I was going to be doing the detection. And I then picked that at a number of millimeters that made my calculations for plate numbers and mobilities and so on very easy. So I picked it at 50 millimeters or 100 millimeters just to help my own spreadsheets later on. And I knew I was always putting my detector at the same spot, which meant that the electropherograms in my thesis looked very, very similar because same field strength, same detection point, you get the same electropherogram coming out. So those kind of little tricks you can get onto the device. And here there's some other benchmarks that were written on. I really like when I've got a spare corner on a mask also to type that it's mine, what it is, and when it was made. Because it may be really useful 5 or 6 years later when you're looking through your drawer. Oh, what was that device for? Ah, it's a 200 micron device with a double T injector. I can still use that. So having a little bit of information on your device, what the design was, may actually help you use it again a couple of years later. So here you can see that device again, a little bit of splashing going on. But again, we get a leakage tight channel being printed by the PolyJet printer. Last printer that we print was our Miniaturised printer. again, you can see that we've taken some action to remove material. In this time, it was not to reduce space, but we're talking 2014, 2015 here. This was at the very early days of 3D printing, and it was really, really a challenge in DLP to get your material to stick to the pick. And the heavier the object was that we printed, the higher the chance that we came back from coffee and the device had fallen into the reservoir. The printer had all gunked up because it continued to project, and we spent half an hour cleaning it out. So we found out that if we actually halve the mass of the device by taking these bits of material out, it makes our life a lot easier because it doesn't fall down. So again, fluidically, the channels here are the same. Designs are different because we took the limitations and the possibilities of the printer into account in making our CAD file. And again, with the reservoirs, you can see a nice microfluidic structure, leakage tiles being printed. So all the designs have exactly the same internal fluidic design, where we've got the inlet channels are 500 micron, the outlet channel is a 750 micron channel. So we didn't want to go too small. We wanted just to characterize and compare apples and apples. The channel depth in all cases is 500 micron. So the closed channels, when we looked with the microscope, that's a bit of a blurry, what's going on? Because with FDM, you deposit the polymer using that thick nozzle. I'm not sure if any of you have ever decorated a cake with a piping bag. Put cream and things on. That is FDM printing. It's a bit smaller scale, but it's the piping bag. So you get all these, toothpaste-like slurs. So you can see the toothpaste coming out of the tube. So you can see that the lay of the material, it's all molten together. So it's leakage tight, but it's not pretty. So the channel width that we got, it was not 750, but 1035. And when we measured, I think we measured 15 devices. So reasonable, repeatable, but a lot bigger than our design stays. Then we look at a microchannel made with the PolyJet printer. Looks very different. First instant, then we think like that's actually looking a lot nicer. Again, this channel, 1000 micron, really good precision. They're only, with 15 devices, only 1.3 micron difference. But we have this weird pattern here. So this is our microchannel. This is the bottom. And we've got this weird pattern here on the structure. That is because every print run, there's a scraper going over the material to make sure the surface is level before the next layer is being printed on. And that scraper leaves some scratches, some imprints on the bottom. So we've got a little bit of a funny texture at the bottom, but the transparency is a lot better. And it looks a lot nicer than the FDM printed material. Then a bit of a surprise. We thought that DLP was great, but then we saw all these square thingies. They are a reflection, an imprint of the mirror, of the digital mirror device. I told you in the explanation that we've got all little mirrors that are reflecting the light. These are all the little squares that we can see here. And all of these squares work as a kind of a point light source, but they're physically separated by a couple of 100 nanometers, which is an area where we don't have any light coming out. So all these little mirrors on the digital mirror device actually come back as single light points where we've got most polymerization happening in the middle and a little bit to the side. The height difference of them is actually not very big, but you can see it when you look under the microscope. You can see the microchannel. And in this case, it was a little bit smaller than we designed. It was 940 micron. Pretty good precision as well. So with the Felix, the side walls were really smooth. So this is the lay of the side walls. That's one print line. The bottom was pretty rough. Eden had this ripped structure in there because of the scraper going on. The Meecraft has got that pixelation, which may also get some mixing effects that I think I'll have in later slides when we try to inject some different fluids in there. When we look at the inlet, Again, FDM is not the tidiest. This is our reservoir. And you can see that the XYZ stage, making a circle with something that only moves in straight lines, is not quite easy. So we've got an inlet width here of about 1500 micron plus or minus 73. With the Eden, that looks a lot nicer and smoother. Again, you project little squares, or no, you inkjet, you deposit the material, so making a circle is easier. And this is where we're projecting. And you can actually very nicely see that our circle is built up from the little squares that we're projecting with. On the digital mirror device, all these square little mirrors become individual light sources, drawing your picture. So you can see the pixelation coming back in the reservoir. Under the microscope, you can see it's a little bit jagged at the edge. It's not round, but if you look from a little bit further distance, it's quite okay. So we can see with the Felix, we've got poor definition and a very rough finishing, because spiraling with an XY stage is not a straightforward thing to do. With the Eden, we've got really, really nice and smooth edges. And with the Micraft, we can see the pixelation, so it's a bit jagged. If we start talking about not an open channel, but a closed channel, we can look at the FDM printer. You can see this really looks like cream out of a piping bag, doesn't it? So you can see that there's some little defects that we could see under the electron microscope. So 250 and 350 microchannels were closed, but could have some deformations. You can see the material. If you look at the SEM, you can really understand what we've seen yesterday, that we get a molten polymer that gets extruded and deposited onto a surface and then solidifies again. It is an extrusion process. Piping cream from a piping bag is also an extrusion process. If we look at the polyjet printed structures, we can see in here the scraper. It really, certainly if we've got a rough edge, we can get a little bit of porosity. One of the papers by Michael Bradmore, they actually used that to make a filter. So that was a really cool idea. But you can see that scraper, that pattern, is being left the roller texture on the surface. We can see that the sealing here was actually really nice. So this is where the closed channels are formed. This is the transition zone from an open channel to a closed channel. And here we can see that, again, the roof has been piped back on. The channels are underneath. And that's where DLP printing really comes up, because we get a really, really nice interface. So where on all the previous images it looked a little bit like the DLP, all looked very crappy and all the pixelated, this is actually a really nice microchannel where this one is open, put a roof on top. Yes, you can see the pixelation, but here you can also see that the high difference actually is relatively minute. There's been a little bit of overexposure, so you can see a little bit of a pillowing effect where the polymerization progresses a little bit into the dark areas as well. So with the Felix, the Felix was the FDM printer. We can see the valley and peak structure that is created by the piping bag. 500 micron was as small as we could get. With the Eden, we've got the rough structure from the roller, but we could make 250 micron channels. And with the Micraft, we had very nice and smooth surfaces. In this case, it was 250 micron channels with straight channel walls. We pushed it a little bit further and we could get down to 100. So we were the first ones to print 100 micron channels. If we look at the surface roughness, with the FDM, we already expected that. It is a piping bag, it is an extrusion-based process. We get significant surface roughness. For the Eden, we can see that structure coming back, and you can see that it's the roughness is about 1.5 micron over that area as a result of that scraper. And then with the DLP printer, we got a much lower roughness of only 0.4 micron. So you can see get a much smoother surface, even though under the optical microscope it didn't look that way. And that's why it's good to also have a profiler to actually quantify how rough a surface is. When we look at the accuracy and the precision, if we design a printer a certain size, how good is the channel that we actually get out? And if we look here, the green points are the Micrafts, the blue ones are the Polyjet, and the red ones are the Felix. First thing we can see on this graph is that we've got kind of different domains in size. The Felix, the red dots, we don't find under the 500 micron channels because we couldn't make them. That's where it's kind of our experimental capability stopped. We can see that with the Eden printer, if our designed channel structure is 250 micron, our realized is just over the 200. So for the Eden printer, we consistently print smaller features than we've got in our drawings. Not a huge problem, because you can correct for that in your design, but you need to know how much smaller your printed structures are than your design structures. The Micraft does it exactly the other way. If we design a 250 micron channel, we print it 400. So it is important to know and measure how big the features are that you print to be able to correct that. The Micraft gets a little bit better when you get bigger, but you can see that there's a significant deviation from the design light width and to the other one. The other thing that is nice and good to look at here is to see that the error bars on the PolyJet, certainly for the largest devices, are really small, whereas for the Micraft they're relatively big. So we got better repeatability with the inkjet printer, with the PolyJet, than we got with the DLP-based printer. If we then start to do microfluidic experiments with them, we still are in the low Reynolds number flow. So we've got laminar flow that we expect. So we looked at two different flow rates, two different Reynolds numbers at the mixing. First with the Felix printed, so the FDM printed devices. What I really like here is that fluids take the easiest pathway. So we've got the yellow dye coming in here, and it sees on the ceiling or the roof on the channel, it sees a flow path. It's a defect, but the dye still goes in. So we can see some mixing taking place here directly. So our mixing in the FDM printed devices is not directly a result of diffusion. We have some other convective processes, and maybe sneakily, we actually have a built-in mixer when we're making an FDM printer. We use that a little bit later. But really nice images here showing what's happening when you've got two flows coming together in a relatively rough surface as you get in an FDM printed material. This kind of carrying along of the fluid along defects is much more pronounced when we increase the flow rate. So here you can see at 10 microliters a minute, we get a little bit of mixing. 25 microliters a minute, we actually get pretty good mixing. This is not as much the case if we go to the PolyJet printed structures. Here again, we've got blue dye and the yellow dye coming in. We can see a little bit of the green forming by that they're mixing, but it's a lot less pronounced than it is when we had in the FDM printed devices. Again, a little bit more mixing happening when we go to higher flow rates. But it is not just a diffusion-based process. And that's probably because we had that roller imprint sitting on the surface that works like the passive mixers that we'd seen on the first or second day of this course. This is where I said during the course things start coming together again. Here we've got the Micraft printed devices. And as you can see, despite being able to still see those little pixelated structures, we actually get a pretty normal laminar flow interface where the green only starts forming here towards the right. Here you can see a little bit more green forming, but we get much less mixing because the surface is a lot smoother. There's not as much disturbance of the fluid flow in our DLP printed structure than there is in our other two printed structures. So from fluidic performance, if you want to have laminar flow and do experiments with that, perhaps your DLP printer is the better one. If we look at the distance it takes, or how much mixing we got for how much distance, we can see that in the Micraft, we got very little mixing. We only got a zone that was 0.2 micron wide by the end of our 25 millimeter long channel. We got near complete mixing for our PolyJet printed structure, and we got pretty much complete mixing for our FDM structures. So you can see that we got really good mixing there taking place, which could be a benefit if you want to have a micro mixer. So if you want to mix, print with an FDM printer. If you want a laminar flow profile, the Eden may be your choice. So it depends on your application, what your microfabrication approach of choice would be in terms of 3D printing hardware. Then we now start talking about post-processing. How much stuffing around is there after my print is finished? With the ABS, there were some little bits of filament sticking out, so minimal, about 5 minutes. When we talk about the PolyJet, we need to first soak it in DI water under agitation, then in sodium hydroxide under ultrasound to remove the support. Then we need to have water pressure to flush it all out. So this is both 2.5. So this should be 6 days. So a lot of post-processing taking place for a PolyJet printer. Very nice printer, very reliable, lots of soaking involved to remove that support material. And then with the Micraft printer, you need to get the unpolymerized resin, get it out. In this case, we're doing with compressed air. We since found that using some isopropanol may be a more effective way to remove the oligomerized resin. The other thing that we did was after the printing, stick the printed devices to a glass slide using some resin and a UV cross-linking station to provide that structural rigidity, because you can print much faster if you only print very shallow structures. So that was the other post-processing that was involved. So if we look at the cost and the fabrication time, our device itself was 4 by 2 centimeters and 6 millimeter high. The Micraft, it's got a relatively small build space. The area where you can print is relatively small. So we could only print one device at a time. If we look at the Eden, the build space is 25 or 25 centimeters, 20 high. Printing one chip takes 30 minutes. Taking 66 chips only takes 2.5 hours. So that's where your scalability of manufacture starts going up. With the Felix, it's a faster print one at a time, even though our build space was a lot larger. So yes, we could print multiple devices, but you didn't really save time by doing so because there was a lot of extra movements of the nozzle. So we tried to have the build space full, but it even took longer. So this is an example of the build space by the Micraft printer, all filled up with the same microfluidic device to print in that 1.5 hour run. So the time that it takes per chip, 12 minutes on the Micraft, 30 minutes on the Eden, 6 on the FDM printed chips. However, if we look at maximum throughput, how many chips we can print with per hour, with the Micraft, we can print 4 in an hour. With the Eden, we can print 30 in an hour. And with the Felix, we can print 10 in an hour. So the number of, the amount of time per chip is not necessarily directly related to the number of chips you can print per hour, because with the PolyJet printer, it is really easy to put multiple devices on the build space. So here you can see all the devices being lined up next to each other to be printed in the build space of the PolyJet printer. If we then look at the cost, and this was an older paper, so it's 2016 prices, but they haven't really moved a lot. Cost of the printer, the Micraft was $3,000. Eden, $85,000. Felix, $1,300. So significant difference in cost entry point of the printers themselves. Talk about the material cost, about $2 per device that we printed here with the Micraft. $4 with the Eden, so it's a relatively expensive material to be printing with the PolyJet printer, and about 10 cents with the FDM printer. So material cost-wise, the FDM printer is really cheap. The hardware is cheap, get a reasonable amount of devices out per hour, and also it only takes 6 minutes to make a chip. Yes, we had some quirky-looking channels, but maybe an FDM is actually not that bad, depending on where your priorities sit. This is the whole analysis that I've just talked you through, all summarized in a single table, where we can see that our resolution, which only scored a 5 or a 6, bit problematic with the FDM. gets a 7 to a 9, 7 for resolution, 9 for precision, because we're really repeatable. So if that's important to you, the scorecard on the report for the Eden is really good. The resolution of the Miniaturised is really good. Accuracy and precision, not as much. So about 7, yeah, we give it about a 7. The material choice, really great on both the FDM printing and the PolyJet. Surface roughness and the microfluidic performance are a bit problematic depending on your application. Same thing for the PolyJet printer. Miniaturised, we've got a very, very different story. We've got the number of materials that's available is actually not that large. They've got a couple of dental resins and things that are microfluidically not even interesting. But then the surface roughness was really good and the microfluidic performance was really good. So if that's important to you and the choice of materials not as much, maybe that's your printer of choice. If we then look at the scalability, certainly don't go DLP. That's not a way of scalable manufacturing. If you want to have scalability, if you want to make tens, hundreds of devices for your project, then your Eden is your way to go. But keep in mind that your post-processing takes a while. You can do it all in batch. So if you make a lot, you can just all soak them in a beaker. It's doable. Post-processing doesn't get much longer if you make larger batches. But it's days. It's up to a week from the finalizing of your print to the point that you can actually use it for your experiment in the lab, which kind of takes that rapid prototyping idea a little bit out of context. Cost, horrendously expensive, moderate, really affordable, both in hardware and in materials. And if we look in time, really high throughput, if we want, especially many devices with the PolyJet, a little bit less so with the Felix and then the Miniaturised. So this table may be useful if you're thinking what printing approach to choose, because every project, every application has got very different requirements. So we've got choices. We've got feature size, which includes the resolution, the accuracy, and the surface properties, which may influence our fluidic behavior. We've got the performance itself, the surface texture, the strength, and the fluidic performance, and chemical compatibility, also an important part. If you don't have a lot of materials to choose from, better make sure that a few materials yet you do have are compatible with the chemistry or the biochemistry you want to do. Material properties, some are off the shelf, some of them are purpose designed, some of them you can't get any information about. Some of them can only print a single material, like the DLP printers, even though I'll be cheating on a little bit later, denying that. Some of them can print multiple materials even in the same run. With FDM printers, you can have multiple nozzles. The inkjet printers by themselves, they're very good at printing multiple materials in one run. Throughput depends on the build space and the print type, and makes some printers more suitable for prototyping, other more suitable for production. Cost is a component of 3 different factors. There's the printer hardware, there's the consumables, which may be your FDM thread, it may be your resin, and it is the time, the manual handling, the labor that's involved in all the processing. And that's also then part in the personal involvement. Can you do it yourself? Is it going to be a service department in your university? Or are you going to outsource it to a specialized print shop? And as I've told you, at my research group, we do it all. We print a lot of things in our own lab, particularly when we do research on the materials. Sometimes we just need a holder printed and we use the university services. For the powder printing, we found that the quality that we get out of a professional lab is a lot better. So we try them all. We reevaluate our standpoint every 2 or 3 years because landscape changes. But if you've got a 3D printing sitting in your lab that's not well suited to a certain task, there's nothing wrong with just asking someone else to print it for you and maybe pay a small fee if it involves a company. Another thing, there's challenges making microfluidic channels. You can also use printables, print processors to accommodate those challenges. So I quite like this approach as a way that us chemists like to cheat our instruments. So this is on a PolyJet printer where this research group got really, really tired and sick of that 6 days of post-processing. So what they did is they used the print pulse print approach, not really to add a component, but they printed the material, did some post-processing to remove the support material, then put a glycerol isopropanol solution on there. Where's my mouse? I need to move my mouse right to get left here on my screen. It's not getting my head around it. So they filled the channels with a glycerol solution, then printed the top on top, and then had a very easy solution to remove out. So they reduced post-processing by actually doing that mid-print. Much easier, accessible, very clever way of cheating an instrument. So what kind of microfluidic structures can you already make? And this is using the Micraft printer. We printed the device for liquid extraction. My headset, my automation off. So here we've got the CAD drawing of the microfluidic device. And what we wanted to do was a liquid extraction from an aqueous phase to an oil-based phase. So we've got an inlet for our organic solvents. Left, yes. So our organic solvents, which was octanol, aqueous solvents, which was water. Here we can see the channel splitting around the reservoir, the inlet of this one, and then recombining to create droplets. We've got the microchannel where we get the droplets going past. You can see on the microscope picture here that we've got the green droplets and the red droplets. One is the oil phase. The other one is the organic solvent phase. So at the intersection here, we get droplets phased. We had two different dyes sitting in our aqueous dye. One of them was lipophilic, one of them was hydrophilic. The lipophilic dye quite quickly extracted into the organic phase, separating our two dyes and only leaving the green dye in our aqueous phase. What we then did is we printed a relatively large chamber where the droplets ended up. And if you're a chemist, you may have done phase separation before, and you know that the dense phase sits on the bottom, the lighter phase sits on the top. Octanol is heavier than water. So here you can see a phase separation. And what we had was two different outlet channels, one sitting here connecting to one reservoir, one sitting here connecting to another reservoir. You can see the two different syringes collecting the outlet of our droplet extractor. One selectively collected the rhodamine solution in the octanol phase. The other one extracted selectively the fluorescent solution that is water soluble and was the aqueous phase. So elegant device, 3D printed microfluidic device for liquid extraction. The benefits that this device has got over devices manufactured any other way, other manufacturer approach don't allow you to have channels at different levels. So having different outlets here is not going to be feasible. We could make holes to put our syringes in. So we had very easy interfacing. We could also connect our tubing with the inlets here. Again, much easier interfacing. Another structure that we made was a microfluidic mixer. This mixer has become famous as the Christmas tree mixer because it looks like a Christmas tree. What it does with the fluids, so we've got two different fluids coming in, a blue one and a pink one. The blue one is a bit harder to see there. Here from the middle, they split up. So you get a little bit of red dye and a little bit of blue dye, and they both branch themselves down, which means that if you start off with a binary inlet of blue and pink, we get increasing amounts of pink when we go from the left to the right, and increasing amounts of blue when we go from the right to the left. So we get a concentration gradient. As you can see with the outlet channels here, we get a concentration gradient moving from pink to blue by combining these fluids of different amounts. We've said before, Reynolds numbers, low Reynolds numbers, mixing is based on diffusion. We need some elements. So all these shoelaces here actually had a split and recombine mixing element printed in there. So the channels will go up and down, forward, recombine again to have more surface interaction to accelerate the diffusive mixing. So that was our little micro mixer that we also used in an essay. And this in here is to prove the point that we can do electrophoresis. So this is our 500 micro channel where we did some isotechophoresis here of different dyes. So you can see the nicely stacked together bands of the fluorescent dyes. So why 3D printing? I hope I convinced you through this lecture going through all the benefits there. The thing that we'll be talking about after lunch is that it's got great potential for functional integration. So after lunch, we will first be talking, we do functional integration now. Okay, all good. Yeah, that's correct, because this afternoon we do something else, and this was a 2-hour lecture slot. So move them around. 10 more minutes before we go for lunch. So if we look at our whole analytical essay, I really thought I was going to read. Reset my mind. Analytical essay. Sampling. I want to get our sample from the big world into our sample reservoir. Sample preparation. Remove the interferences. For example, for solid phase extraction. Essay. Selective reaction or separation. Separation could be chromatography, could be electrophoresis. It could be just in flow injection analysis combination with a selective reagent. And then detection. And we've seen in the first week how many different options we've got available for detection, from the really expensive fancy part, mass spectrometers that Professor Philippe was talking about, down to just using some lines drawn with a pencil as electrodes for electrochemical detection, or just a visual yes-no readout. If we want to do detection, that puts some requirements on the functionalities of our materials. If we want to detect optically, we need transparency. If we want to detect electrochemically, we need a conducting material. If we want to do some solid phase extraction, we need a porous material. If we want to do filtration, we need a porous material. If we want to do chromatography, we need a porous material. Hence our last session today is about making porous materials. I had a hint there. So there's, they have a surface area. So transparency, conducting, porous materials are really important in order to do chemical analysis. Membrane integration is therefore critical if we want to get an analytical sample in answer our device. For sample preparation, filtration is based on the membrane. Solid phase extraction is based on chromatography-based support. Chromatographic separations need a porous support. So porous materials are really important for separations. And if we look at different sizes to get an idea of the pore sizes, sand particles are relatively large, viruses are relatively small, aqueous salts are really, really small. We've seen them with the size mobility trap. But it's good to get a little bit of a feel for how big is big, how small is small, what kind of pore size do I need to stop a cell, stop a virus, stop some sand that may be present in my environmental sample. Integrating a membrane can be done very easily, and I already referred to post-print integration when we're talking about the printers themselves. Here we've got on the bottom a 3D printed device. Post-print, a membrane was integrated, which is a really fancy word for the printed device was taken out and someone came up with a membrane and some glue and stuck them together. That's post-print processing, post-print integration. So the 3D printed device already contains adapters for the syringe pump, channels, and a location where the membrane is going to be inserted. The membrane is manually inserted into the port after the whole device is printed. So you can see a membrane insert. The membrane holding a little frame was just slotted in place and glued in. That was the assembly process. So membrane integrated device. Post-print integration is when we pause the print process to insert the membrane and then continue printing. So We print a frame to do some dialysis. We position the membrane, and we resume the print process. That way the membrane is nicely stuck in place, so we don't need to use that super glue anymore. We have a little bit of manual handling in our print process, but we get here in the printed device, we can do some dialysis experiments with the membrane that we want to use, custom to our dialysis cell where we did do the test with. And in this case, this was also published in analytical chemistry. So that's for enhanced bioaffinity assays. In print integration, and we use the Felix 2, which when I looked this morning was no longer available, but it's been followed up by the Felix 4, times goes quick. And the Felix 4 cost about 140,000 Indian rupees. So not the cheapest of FDM printers, not the most expensive either. The thing that I really like about the Felix is the printer that we saw yesterday. It's got only one spindle sitting to it, even though it's got forward compatibility to have multiple materials. The Felix printer has got 2 print heads sticking out here. Where are they? There. So 2 nozzles, 2 different materials that can be printed at the same time. We found some porous materials, so we worked on some in-print integration. So here we've got a microfluidic device where we printed in a transparent ABS, printed most of the bulk of the device, and then we used a material that was called Leyfeld. And the nice thing about Leyfeld was that if you soaked it in water, it revealed nanoporous structures. So 2 nozzle printer, printed the whole device in ABS, but in the print process, changed nozzles to also lay down a membrane in our Leyfeld in our different material. The reason we did this, that afterwards we wanted to introduce the grease reagents to be able to do an assay for nitride measurements on the other side. So we could introduce the reagents in here. We even went really special that we even printed a lid on the reagent reservoir, so it was all enclosed. So we could even introduce liquid reagents in this one. Most of the time, though, we just printed the devices and we used them. We added the reagents whenever we were going to use it. So Leyfeld, if you print it, if you get it on the spindle, it has no pores. However, if you soak it in water for about 2 or 3 hours, there are 12 nanometer pores that reveal themselves in the material. So we now have a microfluidic device. Looks a little bit like a dog bone, but again, with FDM printing, we like printing less because it takes less time to do so. And here you can see the transparent material containing our microchannels, then a slightly different color, which is our Leyfeld porous membrane, and then another microchannel where we could load our sample into to do our analytical assay. And that's exactly what we did. So here we've got a device, printed a number of devices to be able to work with different concentrations. Again, sometimes it takes a little bit. We could print them at the same time in the build space. Here you can see where we introduce the sample. You can see a little bit of black gunk, and that's because the grease reagent only works with NO2, doesn't work with NO3. So you need to add some zinc dust to your nitride sample to convert the NO3 into NO2 to then be detectable. If you want to have a visual readout or do optical detection, however, that black gunk makes it impossible to detect optically. That's the reason that we included the membrane, because that allowed for the diffusion of our analyte of interest into the reagent to develop its characteristic pink color in absence of the zinc dust that otherwise would have compromised our measurement. So you see the dirt in all of these devices. That's just one of the reagents we needed for the chemical conversion. But we could use our integrated membrane to keep the gunk on one side, do the detection on the other side. As you can see in here, we did the imaging here with the digital camera. Some image processing shows that we got increasing signal intensities, increasing amounts of pink color with increasing concentrations of nitride. nice linear calibration curve, and we collected a soil sample on campus and found 45 ppm of nitrite in the soil in 55 minutes of processing time. So we had a sample in our device that we could just get out of a building, take a little bit of soil, sit outside, have a coffee in the sun, and then get an analytical readout and be able to, with a mobile phone, take the picture, do some pixel processing, end up with a quantitative answer. Michael Britmore and I were reasonably young and ambitious here, so we had a 2-nozzle printer. We saw a new thing coming up at Kickstarter, the 4-nozzle printer. So we very happily went to our students for, look what we found, a 4-nozzle printer. It took 2 weeks to align the 4 nozzles to deposit accurately on the same side. 1-nozzle printer, you guys know, takes a little bit to make sure it finds its home, it's doable. 2 printers is a bit of a challenge. 4 printers, gee, that was hard. They've got a 5-nozzle one as well. We didn't even go there. Our technician and our students would have killed us. So the Rover, nice printer, 4 nozzles. And we did, with a lot of persistence, we did get it to work. So here we've got a microfluidic device. This is about as good as it gets in functional integration. So we've got, I think we use still ABS as our bulk material here. Yeah. So we still have our transparent ABS that we use to print our microfluidic structure. So the bulk material that we can see here, and I don't want to see that yet. The bulk material of the chip holding the channels is printed in ABS. We then have our membrane in the lay felt material that I just already introduced yourself to. We printed that here. The lay felt company also sold lay gel. We had no idea what it was, but we bought it, we looked at it, and it was a membrane with a smaller pore size. So we printed membrane number 2 with a different smaller pore size than membrane number 1. You all may have figured out that I love my electrophoresis. So we also liked to use electrodes. So we can see the black dots here. They're printed in a conducting ABS, and they became our electrodes to drive our separation. So here we've got our device, 2 different membranes and electrodes to do electrophoresis with, printed in 1 print run using a 4 material printer. That took 2 weeks to align, but we didn't say that in the paper. I've talked to you about a size mobility trap, haven't I? We've done this before. 2 membranes, different pore sizes. So indeed, we use this as a size mobility trap. We used our analytes here. So we had a sample reservoir, our sample waste, large porous membrane, small porous membrane, separation channel for some time later. We apply our potential differences. Our sodium, small inorganic ion, it zips through. It fits through the pore, first set of pores. It zips through the other bit of pores. Our target analyte passes our first membrane, too big and bulky to fit up through the second membrane. So it stays in our size mobility trap. Then we've got our proteins in our sample. They are too big and bulky. They don't fit through the first set of pores. So we could do selective electroextraction using size exclusion of our membranes, leaving our proteins and our cell debris behind, our large pore size, so the P+ proteins refers to that. We've got our analyte sitting in our size mobility trap, and we could desalt it because our small inorganic ions are so small that I could still fit through the lay gel material. We use this for the analysis of ampicillin. So here we can see that we had a urine sample with some ampicillin in here. We labeled it with amine selective dye. There's some other amines in urine. So we had in the blank urine, we had an interferences peak of some other small amines being labeled by our fluorescent tag. But using our electrophoretic separation, we could actually separate our ampicillin away from the interferences, and we could get a linear correlation of our ampicillin present in our sample with a functionally integrated 3D printed device. So the device, we have a conducting ABS as electrodes to do electrophoretic separation with. We've got the bulk of the material printed in an ABS to be able to hold our channels. And we've got the lay felt and the lay gel to have two different membranes of different pore sizes to do the sample preparation. We never ventured to larger, more integrated printers. But this is, I think, still the most functionally integrated device that I've seen in literature. So still a really cool project, and I'm really thankful that the people in the lab spent the 2 weeks aligning this printer to make the batch to do this work, to show feasibility. And I'm curious to see if there's any technical improvements to enhance the alignment of FDM printers, because it's a great technology to be using, but it's not straightforward to get on. We're talking, I think this channel is 400 micron wide. With this accuracy, deposit materials from different nozzles in exactly the right location. That's a very hard thing to do. And I hope our engineers will come up with a solution to make that any easier. So now it is lunchtime. Unless you've got any questions. You got any questions, or you're good? So that's one of the things that we've been playing with.
And in FDM printer, sometimes we give support material, and it is wastage of material. So you have any idea to minimize the support material? Then such me and I will work on that.
So there's two different supports. You could use support structures if you've got
support material for support structure.
Yeah, so support structure you can break off. We've done that just in the same materials we use in our print cell to print ABS and do all support structures in ABS as well. We print very simple devices, so practically we don't need support, but if we make all the detectors, we just put it on, print that in the same material and just snap it off and then use a file to make the surface nice and smooth. If you want to remove it from the insides, I would probably check if there's any soluble filaments. So you don't necessarily need to break them out, but you can dissolve them after the print process. If you want to have an internal structure that you want to keep up a roof during the print process and on the roof. So maybe something is water soluble or soluble in alcohol. So I have one filament that's soluble in alcohol, one that's not, and just like that polyjet printer, soak it in alcohol for 1 or 2 days, and soluble one will disappear and the other one stays up.
And is the 4-nozzle printer fabricated in your university?
No, it was came from Kickstarter and was made in Canada. They're selling around 5 printer nozzles per month. So the company is still out there. So if you look for the Rova, ROVA printer, they still got one. I just don't know if that's any easier. That it's an enhanced version that came out, I think, 2 or 3 years after this one. So maybe three will be pretty intense because we go through the fundamental optics of resin development. And to put it in, if you ever will be doing some DLP, it's very useful to know. If you're never going to be DLP, I would say have a little dose. And then after that, I'll be presenting you what is done in DLP on functional integration. There's some cool stuff in there, devices with several and DNA extraction. So second catch will be higher and value than the first one. But if you want to do resin development, you need those fundamentals. So 2 very different exercises. I'll get that downloaded. Thank you. Thanks for coming.
Ma'am,
Yeah,
what kind of examples do you have on last day?
I will talk with you in small groups for 5 minutes to make sure you can pronounce the word of Riddick and say this was a glass chip, and that's not manufacturable, and this was a plastic chip. And therefore,
You know, discuss.
no,